Hello, everyone. Welcome to the Analog Electronic Technology course. In practical amplifier applications, various forms of feedback are always introduced to improve performance. To understand how feedback affects a circuit, we need to study Chapter 5, Feedback Amplifiers. In fact, we've encountered the concept and application of feedback in earlier chapters. For example, when learning about operational amplifiers, we mentioned that negative feedback is essential to achieve linear amplification in practical op-amp applications. In other amplifier configurations like common emitter or common base circuits, feedback is also introduced to stabilize the quiescent operating point and enhance overall performance. To better understand the role of feedback, let's begin with Section 1 of this chapter, Fundamentals of Feedback. So, what is feedback? In reality, the concept of feedback is widely used across various fields. For example, when teachers are giving lessons, they often receive various forms of feedback about their teaching. Based on this feedback, they can continuously adjust and refine their teaching methods to improve the overall quality of education. So, what is feedback in electronic circuits? It refers to the process of taking a portion or all of the output signal, either voltage or current, from a circuit and feeding it back to the input circuit through a feedback network in a specific manner. In essence, it builds a bridge between the output and input, creating a certain relationship between them. An amplifier that incorporates feedback is called a feedback amplifier. This concept can be represented using the following block diagram. Functionally, the block diagram can be divided into two main parts. The upper part is the basic amplifier, which performs the actual amplification. The lower part is the feedback network, which takes part of the output and feeds it back to the input. In the diagram, Xi is the input signal, which can be either voltage or current. XO is the output signal, also either voltage or current. XF is the feedback signal. XID is the input to the basic amplifier, also known as the net input signal, which equals the input signal XM minus the feedback signal XF. Additionally, the gain of the amplifier A is defined as the ratio of the output signal XO to the net input signal XID. The feedback factor F is defined as the ratio of the feedback signal XF to the output signal XO. From this block diagram, we can observe a key characteristic. The signal transmission is unidirectional. Notice that every line in the diagram has a one-way arrow. The input signal is transmitted only through the basic amplifier to the output. This is known as forward transmission. The output signal, in turn, is fed back to the input only through the feedback network. This is known as reverse transmission. In other words, the input signal cannot reach the output via the feedback network, and the output signal cannot return to the input through the basic amplifier. Therefore, in a feedback amplifier, signal flow is strictly one-way. Now, how do we determine whether a given amplifier includes feedback? Based on the block diagram, the key is to check whether the circuit has a feedback network or a feedback path. The feedback path provides the channel for reverse transmission. If there is no feedback path, feedback cannot occur. This condition is called an open loop. If there is a feedback path and feedback can occur, the circuit is in a closed-loop state. Let's take a look at the two circuits below as examples. In circuit A, there is no connection between the output and the input. The signal can only travel in the forward direction, with no reverse transmission. Therefore, this circuit does not have feedback and is considered to be in an open-loop state. In circuit B, the output is connected to the input through resistor R2, creating a feedback path. This means the signal can travel not only forward through the amplifier, but also backward through the feedback network. As a result, this circuit has feedback and is in a closed-loop state. Now let's look at a few more specific circuits to determine whether feedback is present. Take this circuit, for example. It is clearly not a feedback circuit. Although the output is connected to the inverting input of the op-amp through resistor RL, it's important to note that the lower end of this branch is grounded, and the ground potential is always zero. This means the voltage at the inverting input of the op-amp remains constant at zero. In other words, no matter how the output voltage VO changes, it has no effect on the signal at the inverting input. Therefore, this circuit does not have feedback. Now let's look at this circuit. This is a two-stage amplifier. The first stage, or 1, is a voltage follower. Its output is directly connected to its inverting input via a wire, forming a feedback path, known as local feedback. Similarly, the second stage, A2, has its output connected to its inverting input through resistor R5, which also forms a feedback path, and likewise qualifies as local feedback. In addition, the output of A2 is connected to the non-inverting input of A1 through resistor R2. This also creates a feedback path, but since it connects two stages, it is called interstage feedback. Lastly, let's examine this circuit, which is another two-stage amplifier. The first stage is a differential amplifier with a single-ended input and a single-ended output, which then feeds into the second stage, a common emitter amplifier, to produce the final output VO. We can see from the circuit diagram that the output VO is divided by resistors R5 and R6, and the resulting voltage is fed back to the base of transistor T2, the other input of the differential amplifier. This influences the net input signal of the differential stage, which confirms the presence of feedback. Here, the feedback path is formed by R5 and R6. Since the feedback occurs between the two stages, this is also classified as interstage feedback. In this circuit, some of you might be wondering whether the output signal VO can be fed back to the input through the upper and lower power supply lines. The answer is no. And this is an important point to emphasize. When determining whether a feedback path exists, power supply lines and ground lines cannot be considered part of the feedback path because the voltages on these lines are constant. Any changes in the output voltage cannot be transmitted through them to affect the input. Similarly, any variation in output current simply flows back to the power supply through the supply rails. It does not pass through the input circuit. So when analyzing feedback paths, you can safely ignore power supply and ground connections. Through the examples we've just examined, you should now have a good grasp of how to determine whether feedback is present in a circuit. If feedback does exist in a given circuit, what should we focus on when studying that feedback amplifier? We can approach this by revisiting the definition of feedback. Feedback refers to the process of taking part or all of the electrical quantity, voltage or current, from the output side of a circuit and feeding it back to the input side through a feedback network in a specific manner. So, is the feedback signal taken from the output voltage or the output current? This is the first thing we need to determine. Second, how much of the output is fed back, a portion or the entire signal? Third, in what way is the signal extracted from the output? Fourth, how is the signal fed back to the input? The last question is, once the feedback signal reaches the input, does it affect the amplifier's input voltage or input current? In summary, to analyze a feedback amplifier, we need to answer the following questions. Is the feedback taken from output voltage or output current? Is it partial or full feedback? How is the feedback signal extracted? How is it returned to the input? Does it influence the amplifier's net input voltage or net input current? The rest of this chapter will be structured around answering these fundamental questions. In this lesson, we've learned the concept of feedback and how to determine whether a circuit includes feedback. Let's now summarize what we've learned. First, we introduced the definition of feedback, the process of feeding a portion of the output signal back to the input. Next, we presented the block diagram of a feedback amplifier, emphasizing that the input signal is transmitted only through the basic amplifier to the output, known as forward transmission, while the output signal is fed back only through the feedback network to the input, known as reverse transmission. Finally, using specific examples, we demonstrated how to determine whether a circuit has feedback, focusing on whether a feedback network, or feedback path, exists in the circuit. If there is a feedback path, the circuit has feedback and is in a closed-loop state. If there is no feedback path, the circuit has no feedback and is in an open-loop state. That concludes our lesson on the fundamentals of feedback. Thanks for watching.